Good afternoon, everyone. It's 2 o'clock, so I think we should start because the lecture is always packed with lots of interesting stuff. There is a couple of, I guess, questions or a couple of things I wanted to say. The first is I know some of you did not receive a Zoom link apparently for the 6 p.m. meeting. Some of you did. You should get it again at at about 5 p.m. There's an automatic, sending of emails by Zoom 1 hour prior to that particular meeting. Otherwise, I think you can even use this link to join that meeting again, right? So that's the first announcement. The second is there's been some queries on when will be the quiz or questionnaire, and that would be posted sometime after the Friday meeting, maybe on Saturday morning, and then you'll get about 3 days to do it, right? There is an attendance portion to the certificate. I will speak to Nitex and I will come back to you on that. There is a meeting now, as somebody asked if there's a meeting now. There is a meeting now, and there's a seminar or a presentation at 6 o'clock by one of my former students on his career in data science. So without further ado, let me hand it over to Jan.
Hello there. If people can give me just an indication that they can hear me.
I can hear you.
Thanks, Kanshu. Thank you very much for that. Yes, I'm also looking forward to that session and listening in this afternoon. So let me share my screen. Number one.
And while you're busy sharing the screen, let me also just say, if anybody has any questions generally on the programs that we offer at Stellenbosch University, that will be a good time to ask it at that session as well. Great.
Good. Okay, I can see Emila's there as well. Let's get starting. So there are two very different things today on the agenda. I'm going to try and keep it short because I don't necessarily want to repeat everything that's in the notes on the video lecture. So I really want to refer you to those. The first part of today is just going to build on what we had yesterday, and it's probably one of the most important topics, and that's to express the uncertainty in our results. Remember, the whole idea here is that we just have data from a sample from the whole population, but somehow we want to attach meaning to these results so that we can use those results outside of just this little sample that we have. So this very important idea of using the data that we have to try and understand how that fits in, how these statistics that we can calculate for our sample, how that might represent the population at large. So this idea of uncertainty, and there's certainly more than one ways to just express your uncertainty in results. For instance, if you have a mean, you can just calculate the standard deviation around that. You can certainly view that as some form of uncertainty in your results, but we're going to be a bit more robust than that, and we're going to use bootstrap resampling. And you can certainly Google the term bootstrap resampling, and it's a very powerful idea using only the data that we have. So that's going to be the first section. The second session then is going to be on linear modeling. And what I'm going to do in that one is not repeat anything that's in the lectures or notes, and I'm just going to give you some practical experience in Python. For some of you, of course, will know a lot about linear modeling, and I'm just going to show you how to approach it just using one of the very famous packages in Python. So it's going to be jam-packed just with some practical experience in considering how to get the data into your linear models and seeing how you can affect the metrics of that model by adding a variety of our feature variables or our independent variables into that model. So we're going to stick to what we call regression problems. In other words, our dependent variable is going to be a continuous numerical variable. Of course, you can also make those categorical variables and look at logistic regression, etc. But we're going to stick with just the start for those who are not familiar with it. So we're going to have a look at just at linear modeling. So uncertainty in our results, and I've opened this exercise notebook here. So I have compiled all the previous live exercise notebooks, and they are in a zip folder. And I'm sure that you'll be sent those. And then obviously for today, And then tomorrow is going to be a very exciting day, in as much as I'm going to introduce you to a service that is run as a website, specifically for machine learning and to practice your machine learning skills and to take part in competitions. And we're going to look at some actual data, and I'm going to walk you through a machine learning process where we're going to use some real world data, and we're going to solve a real world problem in a very specific field. So remember to sign in tomorrow, where I suppose one of the exciting parts of data science is really machine learning, and it's important to know about that. Of course, in the lectures and in the notes, the three sets of notes in the 2 lectures on machine learning, they are there, so read them and watch them for tomorrow. So back to today, we just want to express uncertainty in our results. So I'm going to work through another example. There are some good examples in the lecture notes as well. So first exercise, we're just going to run this cell so that we just print tables out nicely to the screen. Our very important and old friends, NumPy and pandas. So import NumPy as NP, import pandas as PD. And that looks correct. And then also import the stats module. Import from SciPy import stats. There we go. And then run the code below so that we just save a little bit of time. I think I was getting tired of typing all of these. So we can just run that as just our Plotly Express as usually, and we're just setting that theme that we always use for Plotly. And then we're going to simulate a little experiment again, because we don't have data that we're just going to import here. We're just going to simulate some data, and this would be from some manufacturing process, I suppose. And we're looking at the fracture strength. I'm just going to use that computer variable name fracture strength, and it's going to be taken from a normal distribution with a mean of 30 and a standard deviation of 7. So we see the LOC and the scale arguments there, and the size we want is 80. So this is a simulation of taking at random, taking 80 subjects or 80 samples from a population, for instance, from the manufacturing pipeline, and we're just going to investigate those. And we might be interested in this result because we want to express what we think the whole production line, for instance, is doing, and we've only taken these 80 samples from that. So it's the numpy.random, the random module, of course, normal. And yesterday we spoke about all those, and I hope at least some of you played with all those different distributions. And of course, we're just seeding the pseudo-random number generator. I'm using 28. So every time we run this code, and if you use 28, we're going to get the same pseudo-random numbers. So imagine this is what we're dealing with as a data scientist. We're working somewhere, whatever the case might be, and it is our duty now to look at the results of these 80. So imagine this is data that was now captured from these 80 subjects, these 80 samples from the whole population. And somehow we're going to express a statistic here. We're going to look at the mean, and we need to express what we think, as far as the whole population is concerned, what that mean fracture strength would be. So here we just asked to calculate the mean and the standard deviation. Remember, just a bit of revision, it's numpy.mean, and all these statistics are available just as functions from numpy. So numpy.mean and fracture, I should have actually made it a bit shorter, shouldn't I? And then the other one we want is numpy.std for standard deviation, and that's also fracture length. So you can see is something that I'm doing here that you've seen before, fracture strength. DDOF equals 1. So you can run more than one thing on a single line, putting the comma in, but that is specific to you wanting the results to be returned as a Python tuple. So remember, there are list objects, tuples, and dictionaries. So if you put that comma there, it's going to return a tuple for you. And the other thing to remember here, of course, is always put that we have one single sample, so our degrees of freedom there. We want that to be the sample standard deviation and not the population standard deviation. So from those 80, we see a mean of 22.94. That's from our sample. We have no idea we generally have no idea what the whole population looks like. Only thing we know, as I said yesterday, this is very common. All we know really is the fact that we have data from these 80, and we have to sort of express what we think the real population mean is going to be. So in this instance, mean is going to be our statistic, and we're going to express this uncertainty in this result. And you see that all over the show. If you look at the media, and there's some survey that was done, you express uncertainty in that one specific result that you found. So the next question was just to assign the mean, this mean to a computer variable so that we can reuse it. So let's just do that. And that's numpy.mean again, and it is our fracture strength. There we go. So that's saved now. Let's just see that it prints out properly. Just call that again. And we've saved that 29.994 there. Now with bootstrap resampling, it is very, very important. The idea behind bootstrap resampling, so that we can express these uncertainties, is that we have to resample from our samples to such an extent that our resampled sample size is exactly the same as the original. So if I can just explain it in very simple terms for those, maybe perhaps one person still who doesn't get it. So imagine those 80 numbers, each one of those 80 fracture strengths are written on a piece of paper, 80 individual pieces of paper they put inside of a hat, and you swirl them around. You take one out, you see what the value is, write it down, but you take that piece of paper and you throw it back in the hat, mix it up again, and draw another one until you've drawn 80. And that very realistically means that some of them will be drawn more than once, and some of them won't be drawn at all. And that's the whole idea behind bootstrap resampling, and we call it resampling with replacement. In other words, once that value is selected, you throw it back into the hat, so it is possible, it is equally likely to be chosen again. So in the baseline for bootstrap resampling, this is exactly what we're doing. So one thing is very important is that we know what our sample size was to start off with. So I'm going to save that as a separate computer variable size, and let's call that size so that we can see that it really is 80, because remember we simulated initially 80. So this simulation here has got nothing to do with the bootstrap resampling. This was just us not having data at hand to work with. We haven't gone to a factory and taken 80 samples of the production line and actually looked at these values. So we're just simulating some values there, but we're imagining we've done the study and these are the 80 values that we have. And I reiterate, it's very important that we have exactly the same sample size. And the idea is computational thinking. We've got to convert this idea of a hat with 80 pieces of paper in it, and we resample from it 80 times. Every time, throw it back in the hat, so there's a possibility that it can be selected again. And thus making up this list of 80, we've got to convert that idea into computer code. So create a Python list object called means. So that's what we want, means, and assign 5,000 mean values using bootstrap resampling from the sample. So I'm going to show you it here in two ways. So first of all, we're going to do it the long way, just using a for loop, and so that we can run this for loop 5,000 times over. And the way that we're going to do it, we start with an empty Python list object. Means equals just an empty set of square brackets. That's an empty list at the moment. And then the for loops that we spoke about way back on Monday for I in range, and that I is just a counter, remember? It's just a counter that exists internal to this loop, which means if I wanted to use I again later, it doesn't really exist. I haven't saved it like size exists. There's a little piece of memory that's called size. There's a piece of memory in Google's computer now that holds a value my mean, but this I is just internal to this loop. So it's just used in time in that loop. So let's do the resample. So let's call it something. I'm going to call it a resample. So the range 5,000, remember that means 0, 1, 2, 3, 4, 5, up till 4,999. And that gives us, together with a 0, 5,000 times that this loop is going to run through. So at the moment for I in range 5,000, the first time this loop goes around, it means obviously I is 0. So it's starting at 0. So resample, we're going to make that numpy.random.choice. Remember, that's how we choose from an array or Python list. And what we want to choose from is fracture strength, because that's the array that holds our 80 values. So that's what we want to select from. And how many do we want to select? Size equals, I can put 80 there, but we've already saved it as a computer variable size. And sometimes you see this and it might be confusing. Those two sizes are not the same thing. This is the keyword argument name, and this is the actual computer variable that holds the value 80. So always saying their size is 80, and that is crucial. Size equals size. That is crucial that it is the same size as your original. And then we have to say replace equals true, in as much as for those 80 that are now selected, select one, throw it back in the hat. Select one, throw it back in the hat, as I've explained. So that would be our step. So this I is now 0. We're running through this the first time. It's going to, by replacement resampling, select 80 values for us, and we save those new 80 values as resample. And what we want to calculate, of course, during this first loop is the mean. So let's save that, something separate. So let's say sample mean is going to be that, and that's just int numpy.mean of these new 80 values. And they're not new because they come from my original 80 that we had. And that is resample is what I've called that. So I'm just, let's spell that correctly, resample. So that's just these ones that I've had, numpy.mean.resample. Excellent. And then the last thing I need to do, it's still at I is now still 0. I'm still running through this loop the first time. I'm going to take that empty list that I have there means, and I'm going to append to it. And as I said before, append is just the English term. What it means, append, add something to the end. At the moment, there's nothing in it. So we're going to add this resample mean to that.
Sorry, Jan.
Yeah.
Can you move your screen up a little bit? I think.
Oh, there we go. There we go.
Okay, thank you.
Okay, thanks. So there we go. What's my screen size here? I'm already at 150. Okay. So for
and while you are, oh, okay, I thought you were doing something with the screen. Okay, it's fine. Carry on. Sorry.
Okay. So that is it. So now I is going to be 1. So increases by 1. Now it's the second time this loop runs through, and we're going to just do this bootstrap resampling again, calculate the mean for this new resample, and add a second value to this means. So 5,000 times over, we're going to have 5,000 new means exactly from our original data. And if I didn't make a spelling mistake, that should run completely well. And we do now have these 5,000 values. Let's just check on that. So code, we can just say the length of means, for instance, or means.shape we can use. If we look at length, there's 5,000 values in this list. Of course, I'm just going to show you this one, the alternative, that is just depending on how much goes into your for loop is actually a lot shorter to do. And this idea of list comprehension for those of you who want to do it this way. So on the outside, there's the square brackets right on the outside. So this denotes that we're creating a list here, but we're creating it from list comprehension, and we do it all in one go. So there's my bootstrap resampling right there. I'm passing that resample to the mean function, and I'm doing it for I in range 5,000. I'm doing this list 5,000 times over. So this code is going to do exactly the same as that for loop. It just runs faster, and it is a more succinct sort of code. So once again, we've created possible means, but only from the sample. We have no information about the population whatsoever, other than through this little window that we're looking at, and that is through this window of this 80 samples that we do have. So run the code cell below to generate a histogram of the bootstrap resampled means. And there we go. And of course, it is going to have this shape to it, this bell-shaped curve, this is the idea of a normal distribution. And once again, the mean that we have for our study, we saved it up here, as my mean is 29.99. That was from our study. And if we look at these means down here, that's right up there, of course. But through bootstrap resampling, there was also a probability to find a mean of 29, of 28, and even lower down, or 31 or 32. We are simulating through bootstrap resampling other possible means that could occur around this mean here in the middle. And what we have to do now is to use this idea of percentiles again. And so this represents 5,000 values. And if you remember percentiles and quartiles, quartiles would be the first quartile is the 25% percentile. That means exactly the same thing. The median, or the second quartile, or the 50th percentile means exactly the same thing, those three terms. And then the third quartile, or the 75th percentile. So the percentile is just a more granular breakup of all your values, whereas the quartile breaks it up into 4 equal bits. The percentiles, you can go nuts if you wanted to, but let's keep it as integer values. So 0%, 1%, 2%, 3%, and that just means, so for instance, then for the 50th percentile, so what value in your data set would represent that value such that 50% or half of the values are less than that value. And that's a percentile. So what we're interested in here now is what we call a confidence level. The confidence level, again, is this, what we decide beforehand, how we want to express our uncertainty. And in the notes, in the video lectures, you'll hear me say that in common terms, you'll hear many people say, well, we want to be 95% confident that this mean that we found, that the population mean is within these limits. And that's, of course, not what it is. And once we've run through this, I'll remind you what the correct view of this is. So as we see a histogram here, of course, it is already sorted for us from the smallest possible mean all the way to the largest possible mean. But for these means that we have here, they are not sorted from lowest to highest. And if we want to look at a list of values and we want to see which one would represent a value such that half of the values are less than it, we better sort it in ascending order. And that's what the sort function, of course, does for us. And I'm going to create a new computer variable called means_sort. Kind of makes sense. And we use the numpy.sort function, and we pass these 5,000 means to that. So they're now sorted, and by default, that's going to be in ascending order. So the first one's not going to be the smallest, and then up to the largest one in the end. And if you think about it, they're all in order now. One of them, we're going to be able to make a cut such that a certain percentage of the values are less than that value. And the way we do that is through these percentiles. And if we want the confidence levels, that's something we decide that we want to put in our report, a certain confidence level, we decide on that. Most often you'll see something like 95%. We want to express a 95% confidence interval. So the confidence level is that 95%. The confidence interval is the actual lower and upper bound values. So all we need to do through this resampling is to say, we need to know what value on this histogram here, going from this left-hand side, would be a value of those means such that 2.5% of the values are less than that specific value. So we want the 2.5th percentile value, and we want 97.5 on the other side, because that would represent 2.5% on the left-hand side, 2.5% on the right-hand side. Think about it, 0.25 and 0.975. That's 2.5% and 97.5%. On either tails, that leaves 2.5 on the one side, 2.5 on the other side. Combine them, that's 5%. And if you subtract that from 100, you set with 95%. So what we're actually saying is this middle bit represents 95% of this area under this curve, if this was a probability density function. But the reasoning remains. We want this value of all these possible means such that 2.5% of them are less than, and on the other side, 97.5% are. And that would express this middle 95%, hence our 95% confidence intervals. So all we have to do now really is just to make sure. Now, we did resampling 5,000 times. Now, you can think about the time before computers. If you had to do all this by hand, that'd be crazy, to do this 5,000 times over. You better have a lot of people working with you to help you out, or you better have a lot of time on your hands. Otherwise, this is going to be a daunting task. It's going to take you a while. So we just have to, get the index value. So we have these 5,000 values in order now. And remember, it's a Python list, or even if it's a NumPy array, you can write this code differently. So this is all expressed as a NumPy array. Well, I suppose now that we've used NumPy to sort it, it is now, this means_sort is now a NumPy array. Remember, they all have an index, and they're all sorted from smallest to largest. And the first one will be index 0. That's its little address or its index. The second one will have an index of 1. The third one will have an index of 2. So we just need to know, if we have 5,000 of them, which one in that row of 5,000 would represent the 2.5 percentile value. So I'm just going to call it 2. I think it 2_5 is sort of what I do, just to show that this is the 2.5% value that I'm looking for. And I want integer division, or I want this whole thing just to be represented as an integer. And it's going to be because of the values we have multiplying by 5,000 here. So of course, it's not going to be a problem for us. So 2.5 divided by 100. So that gives us the 0.025, which is exactly what we wanted, but we have to multiply that by 5,000. And I'm going to call it K, just as I did in the notes, I think 97.5. And as I said, that's a bit superfluous, but 97.5 divided by 100 times 5,000. So just think about that. This is going to represent for us. Let's print them to the screen just to make sure everything worked well. 2.5 and K 97.5. And there we go. So if we have this row of 5,000 values in our array, the 120, the one with an index 125 would represent the 2.5 percentile, and the one that's index number 4,875. So of all of these in a row, that one, the 125th one there, remember these are little bins, so it's going to fall in somewhere inside that bin, and all the way, I'm just using it sort of as a real number line here. And the 97.5th percentile will be index number 4,875. Those are the values that we are interested in. So let's just put it here, run the code cell below. So let's just put it here. Let's put it out there. So remember now our lower, let's put it here. I think that's also the same. Just remind me if it's not that what I did in the notes. So it's going to be means sort, the one that I'm interested in, and I'm using index notation. And that's this one, the 125th one. And the upper is going to be means sort. Is it means sort? Is that what I've used? Yeah, means sort. And I want K 97.5. So let's print that lower and that upper to the screen and just make sure that that worked out for us. 28 and 31. So of all these means, if we look at 28.54, which is 28.54, somewhere here, if we draw a line here, 2.5% of the values are less than it. And then on this upper side of 31.4 up here somewhere, 97.5% of the values are less than that. So more than would be the other 2.5%. So through this indexing, we've determined through this idea of percentiles, we've got this lower and the upper limit. And then again, this is just, I copied this from the notes, just this graphical representation of this idea of, sorry, it's very large histogram, very large rectangles, my histogram. So that's a representation of all the possible means there, the resampled means. Here in the middle is the mean that we found, 29.99. And here's our lower fence at 28, oops, where we go, 28.54 and 31.405. So that's the confidence interval. So once again, what does that mean? I want to reiterate that. As it's not that we're 95% confident that the population mean falls between these two confidence intervals, the lower bound and the upper bound. No, it is not. It says that if we did the study 100 times over, so now we will get real different samples every time. If I go to the production line next week and I take 80 samples at random, it's going to be different samples. We're going to get a new mean and we're going to construct new confidence intervals. And if I did this 100 times over, 100 weeks in a row, in 95 of them, the population parameter will be within those bounds. This one that we have right in front of us now, because we only did the study once, we don't know whether that's one of the 95 that actually has the population parameter. In other words, the population mean within those confidence intervals, or if it's one of the 5% that does not. Of course, you know, by probability, nature of probability, you know, it's 95 against 5. So it's highly likely that the population parameter would be between those. And then, of course, you don't have to do 95%. You can do other common ways is to do 80%. So your confidence interval drops, and then these bars will move closer to the green bar, so they'll narrow up. because we're only expressing 80% confidence intervals. Of course, then we're not looking for 2.5 here. The 2.5 there will, we want 10 on either side, 80%, 100% minus 80% is 20%, so 10% on either side. So this will be 10 and 90. So you can decide what you want to do. But this is the whole idea now, that our whole aim with doing this kind of science, the data science project, is that we take a sample, but we can, you know, go bananas on what we do with these, with the data, and we can analyze all sorts of things. But the whole idea is that it must mean something. We must use it to reflect on the population as a whole, because that is what we're reporting to others in an organization, in a research paper, at a conference. Your audience is interested in what that means for the population, for whatever your subject matter is, what it means for the greater population. So we have to express our uncertainty. And it's purely because we don't know what goes on in the population. We only have this information available to us that is within the scope of this data that we have. So the one thing I just wanted to add to this, so I asked there, you know, you can write a little sentence there as to, you know, how would I write this? So I might as well do that. So let me just do numpy.round, and what I want to do is I want to round a couple of things here. What was it? It was my mean, I think, is what we saved it as, and we saved it as lower, and we saved it as upper, and we want decimals. We just want decimals equals 1. In case you're worried about your abilities to round off properly, just pass all of that as a list to the round function of numpy and set the number of decimal places that you want. So in a report, you might put something like this. Let's say the mean fracture strength from this report, or whatever you can say, from this study was, and then what was our mean? It was 30 megapascals, and then I would put in parentheses, say 95% confidence intervals was that 28.5 to 31.4. You know, that would be something that goes in a report or on a paper. You know, this is how we would express it. And what someone who reads that information would take from it, and think that the population, you know, the population parameters probably, you know, within those limits. So that was done through bootstrap resampling, but as you can well imagine, there are equations for these things, and you can write a bit of code and do all of that without resampling. But I think it's very important for everyone to have a very firm grasp of this concept of bootstrap resampling, because we do use it a lot. So what we've done here, I'm just showing you through a bit of LaTeX code. Remember, if you click on these, you'll see how the LaTeX code is done between these little double dollar symbols. So this SE here, that stands for the standard error. And the standard error is the sample standard deviation S divided by the square root of the sample size. So you just calculate the standard error. So the standard error is expressed in terms of the square of your sample size. And then you want to know a certain fraction of that standard error. And these are things, if you still have an old statistics textbook, and you'll find these in tables at the back of the book usually. And it'll have tables for Z distributions, which is our standard normal distribution. The T distribution, you'll have all of these. So you want to know for 95%, or then the alpha value 0.05, what that T value would be if we use a T distribution, which we are going to use here because we're dealing with a sample. We don't know what the standard deviation in the population is. And then usually for 95% confidence intervals, you can look up in that table what the T value is going to be. And you just multiply that by the standard deviation. And that's how you can calculate confidence intervals. So what I've done here for you is just T_4_95. So T for 95% confidence interval. There's this PPF function. So it's stats.t as my type of distribution I'm using. It's PPF, and I'm just showing you there without a long explanation of why that is so. 1 plus the 0.95 that we're interested in divided by 2. And the second argument that it's going to take is this 80 is our sample. We have a single group, so the degrees of freedom there is going to be 79. And that works out this little t, but as I say, you can look that up in the back of a statistics textbook. And then we're going to create this standard error. And that, as I said, it's the standard deviation divided by the square root. And if you don't want to do that, there's also a stats.sem function and fracture. If you do that, it's going to do that calculation for you. And that gives us this h, which is now t times the standard error. And all you have to do now is subtract it from the mean, and you add it to the mean, and you're going to get those results that we had before. So this would be a parametric way to go about it. In other words, we are using parameters from a known distribution, a described, defined distribution, and we calculate these confidence intervals from that. And in a whole separate way of doing it without being concerned about any kind of parameter. So we're not concerned here. We're not using a parameter from a known distribution. We're using bootstrap resampling. And as I said, it's very important, I think, for everyone to know about this concept of bootstrap resampling. And then, of course, in the notes, you'll see on the video lectures here, I do it for median as well, just to give you some more information on that. So for me, that's it for uncertainty. Express uncertainty in your results. The main idea that I want to leave you with is, in using the scientific method, is that, and as scientists, our trust in absolutes is just not there. We have to express our uncertainty in our results. We have to tell others, we have to give others this interval, and we can use different intervals than just these, not only to reflect, what we think the population looks like, but of course that's the main idea, is what does the population, what do these results mean as far as the population is concerned? That is where we want to use the results of this data science project that we are dealing with. I want to move on to the linear modeling. And as I said, this is going to be a much more practical approach, and I want to show you, showcase just how easy things can be in Python. Because linear modeling itself, anyone who's taken classes in that formally at university know, I mean, this is a massive, massive big topic, and there's certainly no way for us to cover it very quickly. And so I want to leave you with an idea of just how easy things can be in Python, and we're going to make use of one of the two major packages in the Python ecosystem, and that's called stats models. So if you Google stats models and you go to their website, they've got brilliant documentation, all sorts of examples, especially if you're quite mature in the use of linear models, you can certainly go have a look there. The alternative to that, of course, is called scikit-learn. So scikit-learn, let me just write it out here on the screen if anyone wants to Google that. Let's put it there. So it's scikit-learn, that's the name of the library. And you can certainly Google that. And that's another library to deal with modeling. And it goes beyond what the stats models can do, in as much as there's a lot of machine learning built into scikit-learn. And that's where we would use what most of us in data science use scikit-learn for, is its machine learning ability, but it can do linear modeling as well. So I'm going to show you stats models specifically for generalized linear models. And so let's get going. So I hope you've watched the video lecture, or at least read the notes or played with a notebook, so that you understand this idea of least squares, at least. How are we building this line by minimizing the error that we make? So I don't want to rehash that. Please go through the notes, play with that notebook, or watch the video lecture. And of course, I've got other resources available if you want to delve deeper into linear models and how we use regularization and all sorts of other more advanced ideas. This is about the concept of it. So let's run that cell as well. Let's quickly import pandas as numpy as numpy. Don't know why I asked in these exercises to redo this every time. It's PD. So we've run that. And from scipy import stats. That's just a bit of useless coding there. So run the code cell below to import the make regression function from the scikit-learn package. And what we're going to do here, I think in this one, yeah, we're going to make, again, simulate just our own data so that we don't have to import a CSV file, etc. And so this scikit-learn, if you import it, you don't type scikit-learn. There's sort of already an abbreviation if you import this into Python. It's actually called sklearn when you do the import, not scikit-learn, but that's exactly the same thing. It has a module called datasets, and it's a wonderful sort of module. You can do all sorts of things, a very interesting module. And it has a function called make regression, and there's another function called make blobs, and there's another function called make classification. And it's very nice for you to simulate your own data. So when you do research on machine learning, for instance, deep neural networks, you just want to generate this data that you have absolute control over in many instances because you're interested in researching something new about neural networks or other machine learning algorithms that you have control over the data that you bring in. You can just make your own data here. And then, so that's what I'm going to use scikit-learn here for. And it's an interesting thing to do. So, and then we're going to use stats models. So there's a bunch of modules inside of stats modules. I'm going to use the easiest one. And the reason why it's so popular is because if you want to use the R language, another great language for data science, the R language allows us to write these little formulas. And what stats model does, and that's very popular to do, and one of the successes of R is this formula.api module allows us to write code that looks almost exactly like R. So for someone like myself that uses both R and Python intermittently, even on the same project, sort of just a nice shortcut as this module. So we'll use that one. So this one is just for us to graph. I hope some of you have watched my video on matplotlib and found that interesting. And then another library that you can check out for plotting specifically in data science is Seaborn. Seaborn has just come out with a new release. I think it's version 0.11, and they've made some terrific changes because Seaborn is not a library that I use too often. But I see they've made some great changes there in Sydney. It might be that I start picking up the use of Seaborn again, and we usually import that with a namespace abbreviation SNS. So check out Seaborn as well. And the whole idea of Seaborn is that it sits on top of matplotlib, and it just makes it easier to use matplotlib, basically. It smooths things over a little bit because if you've seen the video on matplotlib, you'll certainly know it's an enormous, enormous package. And Seaborn just makes some of the coding in matplotlib a little bit easier. So specifically geared towards making plots in data science. So yeah, we've imported that. And now we're going to use this make regression function. And as I said, it's a wonderful thing because you can control how you design your data. And I've used a couple of the arguments. You saw there that it has a bunch of arguments. The first one that I'm going to use this is the n_samples. And I set that to 1,000 because I wanted to generate 1,000 data on 1,000 subjects for me. So if you think about a spreadsheet file, that's 1,000 rows of data. I want 5 features. So I'm setting n features equals 5. And n informative is 3. So I'm saying 2 of those features are not going to really contribute to the solution to my problem here. And let's just think about real life scenario. We propose some data science project or some research project, and we have our research questions. And as far as modeling is concerned, at least, we'll have this one variable. Of course, you can have more than one, but let's just keep it simple. We're going to have this one of our variables is the one that we're trying to predict. We're trying to build a model to predict the value of that variable, given all these others. So in statistical terms, we'll call the first lot our independent variables, and the one that we're trying to model or predict is called the dependent variable. That variable depends on the other variables. And tomorrow when we talk about machine learning, we use quite different terms there. We'll call those independent variables, we'll call them features, feature variables, also call them predictor variables. And then the dependent variable, we usually call them an outcome variable or a target variable. Specifically in deep learning, we use the terms feature and target, but you can also use those other terms. So it's just different words with the exact same definition, basically. So what I'm saying here, again, in the real world scenario, we decide that we think that these variables, and we might be domain experts, or we've read some other published papers on this, or we have some industry experience, and we know these variables should be explanatory as far as this target variable, this dependent variable is concerned. So we're going to collect data on those. We can use those, the values for those variables, to build a model to give us this dependent variable value. But in many instances, if you're doing brand new types of research, we're not 100% sure about this, and that's why we build, that's why we do this. And it might very well be that some of the variables that you are collecting doesn't really help at all. They're just not informative as far as helping a model to predict the value for the dependent variable. That's quite normal to do. So here in this make regression function, we can actually simulate that. So I'm going to say n informative equals 3. So only 3 of my variables are really informative when it comes to what the dependent variable value is going to be. And then there's this random underscore state. And if you set that to some integer value, every time you run this, you're going to get different values. Now, this make regression function, as I say, there's also a make regression, and there's a make moons as well. All sorts of models that you can create that introduces a lot of non-linearity. So if you know a little bit about linear modeling, you know what we have to do if a linear model is not going to suffice, that there's non-linearity in our model. So there's all these functions in scikit-learn. So you can generate some really interesting data to make life very difficult for your models that you build. And if you try out different modeling architectures, you get more success or less success looking at the metrics of your model. So that's what the make regression is going to do, and it's going to generate for us 2 NumPy. This function returns 2 NumPy arrays, and so we've got to assign that to 2 different things. The first one is this matrix, so rows and columns of our independent variables, and so that's going to have 5 columns and 1,000 rows. And then the y, and we usually use uppercase x and lowercase y, sort of to fit in with statistics textbooks and all the symbols that are commonly used in this domain. So it's usually uppercase x, lowercase y, but you can call them whatever you want. And so that's going to be our feature matrix, or our matrix, rows and columns of independent variables, and our vector, because it's just a single column, of our dependent variable, so x comma y. And all I'm doing here is I'm just building that into a data frame. So I'm going to say df is the name of my data frame, pd.data frame. And before, you've seen we've used Python dictionaries to generate values for data frame. Here's another way to generate a data frame. So I'm passing this matrix, rows and columns, 1,000 rows, 5 columns of values I'm passing to my data frame. And now by hand, I've got to type in what the column headers are. So if you think of a spreadsheet, that first row that contains all the column headers or the variable names, I've got to generate all of them, and I'm passing that as a Python list object to the columns argument. So columns equals, and just to be generic, to be abstract here, I'm just going to call them var A, var B, all the way to var E. So that's my 5 variables, and whatever field you're in, you can let your imagination run wild as far as what these are concerned. And remember, now that I have my data frame, I can always add a new column to that. So df, and then in square brackets, and then because it is a string, in quotation marks, and I'm going to add this y, this extra column to that, so that I now have 6 columns in the end. So let's just do that. And as I said, depending on what field you work, if you want to control over the design of your data, and you don't necessarily have data to go out there to work with, this is a brilliant way. Look at that scikit-learn package and see what all this different data is that you can simulate. And there we have our data frame object, var A, var B, all the way to var E, and target right at the end. And it's going to be 1,000 simulate values, data point values for 1,000 subjects along these 5 independent variables, and then one dependent variable that I've called target here, just because I'm so used to working in the machine learning field that I've called it target instead of dependent. So there we go. Now, just as a sort of a little tip here for you. So most of the time, well, in reality, you're not going to work with things this way. This is for you to experiment with. You're going to import a CSV file, and then as a data frame, and you want to actually extract from your data frame, you want to extract NumPy arrays, because there's a lot, there's a lot of fine, nice, finicky things you can do to NumPy arrays that you can't always do with a data frame. So sometimes you want to extract the NumPy arrays from your data frames. I'm just showing you here how to do that. So just to get back to a matrix or a NumPy array along 2 dimensions, in other words, rows and columns. So I'm going back to X and back to Y. And if I only want those values, these first 5 variables, I'm going to say df.drop. Remember that deletes the columns. So I'm saying delete the target column. And axis equals 1s means look along these columns. Axis 0 means look along the rows. So axis equals 1s look along the columns. So it's going to look for this target up here along the columns. So it's going to drop that one. And then I use this method here, .to_numpy, open close parentheses. So that's going to convert those first 5 columns into a NumPy array. Now, remember, I think before I showed you, there's another little argument called in place equals true. If you set that, then that's a permanent deletion. We don't want a permanent deletion. We don't want to change our data frame, so we don't put that in here. So this X is now going to be just a matrix you can think of these 1000 by 5, 1000 rows and 5 columns of data. And then, of course, Y, I just want it to be df.target, that pandas series object. And to strip away the index, so to actually just have an array, it's again, use this method .to_numpy. And if I ran that, I'm back with the X and Y. As I said, sometimes it's very useful rather to work with NumPy arrays than with a data frame object. So I'm just showing you here how to, how to do those 2 things. So in that lecture on linear modeling, we start off by just looking at correlation. And I think everyone intuitively has this idea of what correlation is. So when we compared the means to each other, that was the same variable broken up by the sample space elements of a categorical variable. So we created these groups from the sample space elements of a categorical variable that gave us different groups. But what we're comparing is the same continuous numerical variable in both of these. Now, that's not what we do in correlation, and that's not what we do in linear regression. We're talking in simple terms here about a continuous numerical variable against a continuous numerical variable. So if I've got 2 continuous numerical variables, I'm looking subject by subject, so row by row, and each one of the rows, for each one of the subjects, I'll have a pair of values, one from the one variable, one from the other variable. And it's that comparison, that correlation between those 2 that we're looking at here. So to do that, the easiest way to do that, and there are many ways in Python to do that, so this would just be one way. I'm just going to create use my data frame, because the pandas has a lovely function called CORR for correlation, and that's going to give us back a data frame object, and I've called it CORR for obvious reasons, and that gives us this correlation matrix. So here I can see all the pairs. So first of all, variable A with variable A, well, that's going to have absolute lovely correlation, because it's just the pairs of values look exactly the same for all my subjects. And our correlation is going to go from -1, remember the intervals from -1 to +1. +1 is absolute positive correlation. As the one value changes, so does the other value change for the 2 variables. They're in step with their changes. And of course, every variable would be, and that's why along this main diagonal, that's what we would call this for a matrix, along this main diagonal, 1, 1, 1, 1, you see it all the way down. But now I can read from the left or from the top, variable A with variable B, that would be that -0.03 up here. That would be its correlation coefficient there. So it's nearly 0. So there's very poor correlation between A and B. And the same there for C, and the same for A with D, and the same for A with E. And with the target, that's the one we're interested in. Because when we look at building a model, one of the first things we want to do just here is look at these, how well are these numerical variables correlated with the target. Now, in machine learning, we'll call this a regression problem, in statistics as well, because our target here is a continuous numerical variable. If it was a categorical variable, in machine learning, we'll call that a classification problem. In statistics, we might tackle this problem using logistic regression. Anyway, we can see here that variable A, anyway, has a quite a nice correlation with the target. Not so much for B, not so much for C at all, also almost zero. Very good for target D, it's up to into the 0.71, and then very poor again for target E. So we've already got this idea that that A and B are very well correlated. Now there's a lot of deeper things here. We've got to look at things called like multicollinearity. If you look at the linear algebra, for instance, behind ordinary least squares, and you take the transpose of a matrix times a matrix, that gives you a symmetric matrix. But if your columns are not independent, you're struggling with multicollinearity and you can't use that equation. So that's some deep mathematics there, and I'm not going to get into any of those. Our data set here is well behaved. We don't have to worry about any of those things. Forget what I've said. We're just dealing with the basic concepts here. Now, of course, we can look at this set of numbers. Sometimes it's quite big. We have many variables to deal with, and then it gets difficult to stay at a bunch of numbers, as we said right on Monday. So I can create what's called the heat map. So run this code cell below. So in Seaborn, there's this nice function called heat map. I think there's many new parts to it now, but I'm passing my correlation matrix here, which is actually now a data frame. I'm setting it to be square. And I'm using a color map, plasma. Plasma is this dark blue to light yellow. There are plenty of these named color maps. You can go, you can use any of them. And again, it's variable A against variable A, B against B, and that's white right up here at the yellow, which is 1.0, and then all the way down here would be 0. So of course, on the main diagonal, we're going to find the yellows because they're perfectly correlated. And now we can quickly see this idea of A and D. You know, they're higher up on this color scale, and B as well. And remember when I designed this using make_regression, I said 3 of them have to be contributory to the target variable. And you can see there's A, B, and D. I mean, B is not so much, but at least it's up there, but definitely C and or C and E, you know, the correlation with the target variable is very, very low. And that purely comes from the fact that I said here, informative must be 3. So you can see what I mean by having control over the design. If the idea is really not so much behind the data, but you're studying the actual modeling, doing research on the model side and new models, new machine learning algorithms, etc. It's nice to have the ability just initially at least to be able to generate these. So I find it useful from time to time. So visually here, we get an idea of which of our variables are correlated with other variables. And of course, in the lecture notes, in the video, in the notebooks, you'll see me delve into this a little bit deeper. So I said their variable A and D, they seem to be most strongly correlated to the dependent variable target. So run the code cell below, and we're just going to look at a scatter plot. This time it's var A against the target. So again, just to showcase, because this new version of SNS came along just the other day, so I'm interested in just re-looking at it because I haven't used it for so long. So there's this LM plot, linear model plot function, and it's a scatter plot. So we're going to do var A on the x-axis and target on the y-axis. So you see all these pairs of values. So each one of these markers, quite obviously, pertains to one subject, and it's a pair of values on the x-axis, y-axis. And what this linear model plot does, it already puts a model for us there. You can see the blue line running across. So what a model means is, if someone had a var A value of 2, you go up in the 2 until you hit the line, go across, the model would predict here, around about there where my cursor is. I don't know if you can see my cursor just above 100, what the target would be. So I only know the value for var A. After my research, I can predict, I can use this calculation from my model to know what to predict sort of what the target is going to be. And this linear model plot already puts that the best fit line through there for us. So it's a nice thing to do, and you can play around with that and put D in and have a look at all of those. So now comes the little practical part. This first one you would have already seen in the notes, and that's where I asked you just to use this stats models to create a linear model. And this is a simple, single variable linear regression model. So I think I've asked there to call it uni model. So uni model. So let's call it that. And all we want to do is to use Python code to build this model for us. So we imported that formula.api submodule from stats models as SMF we did. And then the function is OLS. If you don't do the Formula 1, it's OLS with uppercase, but here with the Formula 1, it's lowercase. I don't know why they made that distinction, but sometimes I put uppercase there, and it's always wrong. It's always the lowercase one with this formula. And then we can just write the formula equals. And the formula goes inside of quotation marks. So it's very much similar to what we do in the R language. And as I say, that's why I think many people will default to using this module. So all I can write now is a little, almost English sentence formula. I'm saying the target, build for me a model that will predict the target given, and that little tilde symbol, find it on your keyboard. On my MacBook Pro here, it's Shift right next to the left Shift key. And all I want is for it to use var a. So I'm saying, build me a model that predict the target variable value only given var a. That's it. I've got to tell it where this data comes from. It comes from the DF data frame. And then I've just got to fit the model. So this is going to build all the parameters of the model for me. And then I fit those to the model. So just remember to put that dot fit. You can do this in 2 steps, but I usually just do it in 1. And then we can say unimodel dot summary. There's also a summary too, and it prints to the screen a little different, but let's just use summary. And if I didn't do anything wrong, we get this beautiful report. So let's just go through that. It gives us a beautiful report here. At the top, you'll see R squared and then the adjusted R squared. So you can think of those of the fact that, of course, I can build many variables into my model. And eventually, you've sort of got to penalize against those. So it'll adjust the R squared for us. And so what is this R squared? We see that's 44.3. So in very simple terms is what we're saying is my model. So if I have values for variable A, it explains 44.3% of the variance in the target variable value. So if I just looked at target variable and I did df.target.var, it's going to give us the variance in the target model. So my model predicts 44.3% of the variance in the target variable value. That's not too bad. It's not too good. But we can certainly do better. So that's what we get from there. I talked a little bit about F distribution in the lectures. And so you can see my F statistic there. So go have a look at that. We also get a probability for this F statistic, which is much lower than 0.05. That's what we can see there. And I just want to tell you a little bit about these two, the AIC specifically, ICARCE, I hope I'm pronouncing that correctly, information criterion. And if you really want to pursue some interesting research, go look at information theory. Information theory is just one of those very exciting things, Shannon entropy, all those kind of things, very interesting thing. And that's this idea of, the information in a system and how many bits do I have to use to explain the system. So what you want to see when you build these models for you to improve, of course, we use that in logistic regression. That would be our metric that we go after here. We're sort of more interested in the R squared, but you want this value to come down. The lower these information criteria are, the less information, the less explanation you have to require to show this information that you do have. I'm not expressing myself properly. So you want this just to be as low as, you want it to get lower as you build new models. That's an indication that your model is doing better. That's for logistic regression. So let's concentrate here at the moment. We want to improve that R squared. And the R squared, R squared will go from 0 to 1. 0 means, you're explaining 0% of the variance. And in the notes, I show you where you build a very simplistic model using the mean of your target variable as your predictor, and how we contrast that to this best fit line to express and understand all of these things. What I want to reiterate here and repeat here is, what have we done? What does a linear model mean? So forgive me if this is a bit simplistic, and of course you understand all of this, but I just want to stress the point. So this first value that I have here, this column, 1.19, 0.57, 0.17, these are the first couple of values in my var 0. And if you look at ordinary least squares, of course, your matrix that you build does have to have that first column of zeros in it, because there are 2 parameters that we're after here. We're after the slope, that's that value, and the y-intercept. So we actually need to calculate these 2 parameters. Go look at the notes, go watch the video to understand that. So what we're saying here, and that we can see that in the model here, before I forget, there under coefficients, that's what we're after. There's our y-intercept. So when x is 0, so when our var A is 0, that's going to be the prediction and for our target variable. And that's the slope of the line, because this line here, it's a straight line. Remember from school, y equals mx plus b, or y equals mx plus a. The m is the slope, rise over run, and the c is the intercept when x equals 0. So there's our two coefficients. And what we're saying is, it's this coefficient for var A, which is 74.77. If I took that 74.77 and I multiply it by 1.19 and minus, so just again, a little bit of linear algebra, I'm going off at great tangents here. This is a vector and this is a vector. Oops, just this first column. This is a scalar, and if you multiply a scalar by a vector, it just means you multiply that value by each one of those separately. So 74.77 times 1.19, 74.77 times 0.57. And the same here, it's minus 4.56, which comes from right there. You multiply that with 1, and it's just going to be minus 4.57. So 74.77 times 1.19 minus 4.56 is approximately, and this is our target variable values, the first 5. If you go look initially at the data frame, those, unless I've made a little retyping error there, that's got to be that value. So our model is trying to predict that value. Of course, it's not going to get there. It's not going to get there. We're trying to be as close as is possible. Hence, we see that little approximate symbol there. If I just double click on that, you can see how to write the LaTeX code for all of that. So that's what a model says. This is what we're trying to build. We want to try and get as close to those variables. We want to minimize the cost function. And again, I refer you to the lectures to understand this idea of the cost function. Okay, so that's about the information there. And there's all sorts of, if you get deeper into linear modeling, there's all these things here that, quite interesting and quite important. And you can go have a look at those. So let's create a scatter plot to show the actual values against the predicted values, because that's what we're after here. So why do we build these models? It might very well be that it's very expensive or difficult to get the target variable value, and it's easier for us to build a model so that we can get these easy to understand and collect the values, to calculate this value. That's a simplistic way. There's lots of reasons to build these models. So what I'm going to do here is let's just create a little scatter plot just to see our actual values, our target variable values, our dependent variable values against the predicted ones. It's very nice always to visualize this. First of all, I've created this model now called uni_model. What did I call it? Uni_model. I've got to create predictions from it, and there's a nice method. So if I say uni_model.predict, so that predict function is actually now going to use those two parameters, those two coefficients, do that calculation. And of course, it's going to do 74.77 times 1.19 minus 4.56 is not going to be 76, it's something else. So it's that calculation that I'm after now. What does my model, this side of my model, what does the calculation predict? Because I want to visualize that prediction against the actual values. So that predict method is going to do those calculations for us. And let's go very quickly over this. I suppose it's good just to see how to do a graph like this again. So I would always say go.figure. And then we can just add, this my blank canvas, remember, from Plotly, and I can add traces to that. So fig.add trace. What do I want to add? I want to add a scatter plot. And what do I want on my x-axis? Well, I want the actual values. Remember, that was y. And on my y-axis, I want the predicted values, and I've just calculated those up there, y_pred. So it's going to be the actual values against the predicted values. At the moment, that's going to give awful lines. So I've just got to set the mode to markers, because I just want obviously the little dots. And let's do that. And then, of course, I'm just going to run that. But of course, we want to do a fig and then update the layout to give a title, a nice little x-axis label and a y-axis label, and make it look all pretty. But there we go. On the x-axis, we have the actual values, and on the y-axis, the predicted values. So you see that model is not too bad. And that's expressed by the fact that we've got an R squared there of 0.44 3. And if one nice thing about Plotly and why I use it is that, I can hover over any one of those, say there. Well, let's take a sort of a better one there, more towards the middle. So for that particular true value was 87.65982, and the model predicted it to be 69.54. And as I said, the other thing is with Plotly, of course, I can zoom in, and it makes it nice and interactive. So I can zoom in, and then I can, if I get the right tool, the pan tool, I can move around, and you can imagine that there are some plots that you can generate that this might be quite helpful during a presentation, etc. And also when you have meetings with your collaborators, it's always a nice to do. So the next one here says create a multivariable linear model using var A and var D as independent variables. Assign the model to a computer variable called multi-model. So let's do that quickly. So this you would have seen in the notes, but smf.ols. And again, I just want to build an easy formula because we're using this SMF, this formula API, and I want that just to be target once again. And so model for me is please the target and use var A and use var D. And the way that we add, just in simple linear terms, this is a linear model. So I'm just putting the plus sign there. Just add these two. I've got to say data equals, comes from df, of course. And then always remember that just builds the model, but I've got to fit my data to my model. So remember the dot fit, and then call it the summary on this multi-model of ours, multi_model dot summary. And if I made no mistakes, there we go. So of course, what we're now going to see is a different intercept. It's still there. And now we've got value for var A and for var D, because we actually now have a surface. It's no longer a line. And so, there's more dimensions that we bring into the problem. And look what's happened to our R squared. That's very high, 96%. So my model as it stands explains 96% of the variance in the target variable. That's extremely good. And you can see the very high F statistic there. I mean, by approximation, the probability is tiny. And you can see also my information criteria has come down. What was the information criteria before? 1.1 times 10 to the power 4. And now we've gone down to only 9,000. So we've improved. And of course, for our purposes here, our R squared has improved tremendously. So once again, apologies for the simplicity here, but I want to bring the point down. What we're saying now is, here's our coefficients. So I'm saying 75.35 times var 1 plus 84.3 times var 2 plus 1.1, and just multiply by 1 is that is going to approximate 76.95. Of course, the actual value is going to be slightly different, but this is what we mean by a linear model. So it's all these coefficients times those variable values, and again, just add the intercept there. So I've already typed it here, so we can just look at. So remember what we got out here. Remember what this looked like. So let's look at our better model. We've improved things now. So I've got a new YPRET there. It's multi_model. It's my new model. And then that's what we did before. I've just added a little bit nicer. I've put some size and opacity to the markers, and I've put the layouts as well. Otherwise, it's exactly the same. And look at that, the actual values versus the predicted values. Now, how have we improved things from that model to this model? And all it took, was that one line of code. And that's really brilliant to do when you start exploring the data sets that you're working with. So the next one I want to show you, and as I said, this is just so that we can, so that I can show you how easy it is. This is much more of a practical little session that I'm trying to have here. So add an interaction between A and D. So now we're going for interaction between terms, and we're just doing multiplicative interaction between terms. So what that means mathematically is we multiply those two values with each other. And again, if you know about linear modeling, you'll understand when that becomes important and useful. So smf.ols, and we have our formula. And so let's build this formula just so you can see just how easy that is if you haven't seen it before. So again, that's my target variable, and I want var a plus var d, and now I want to add to that this interaction between those two. So I'm going to say var a multiplied by var d. So I've got these together with my intercept. I've got these three things now predicting target: var a, var d, and the interaction. And I'm saying data equals df. Oops, I've got to put that outside of those. Data equals df. And remember that builds it for me, but I've got to fit my data to that. So let's look at intermodel dot summary. So let's have a look at this. And there we go. We haven't increased our R squared really. And we went from 90, our information criteria, that didn't shift really at all. So, when you start by the knowledge that you have of your field, when you start generating these models, these are some of the processes that you might want to follow. So that, by example here, just in this short time that we do have, that's how you would do multiplicative interaction between those two. And what have I got here? Oh, okay, so I'm just using ypred intermodel predicted so that we can look at what that looks like. And of course, we're not going to see much difference there between the actual values and the predicted values. So next up, you might want to not do multiplicative interactivity, but you actually want to transform some of your variables. That's the way you apply a function to one or more of your variables. So in this instance, we asked to add a logarithm transform of the square. That's horribly spelled there. I'm sure there's been, as I said before, correct the spelling errors and syntax errors in your notes. Add a logarithm transform of the square of variable b to the model above and assign it to, oh, too many mistakes. Let's just do it. So we're going to do func model is what we asked to do. So once again, that's very easy. It is going to be smf.ols, and we've got formula equals. So let's build this. It's target. Oops, those are the wrong little tick marks there. It's single quotation marks, target. And then according to the following, what does it ask for? A logarithmic transform, the logarithm transform of this, that's just wrong. I don't know why that is there. So, all right, let's fix all of this. Add a logarithm transform of the square of variable b. No, that's quite correct. That is what I wanted. So when we used that make regression, it normalized the values for us. So remember before we spoke about that, expressed them in terms of standard deviation. So there's some negatives in there and positives. So you can't take the log of a negative number. So one way to go about that, one possible way would just be to square that value. Any value squared gives you a positive. So I'm going to have var a still plus var b. And now I want to add to that this logarithm transform of the square of var b. And inside of this, even though it's a string, I can still say numpy.log. And what do I want to take the log of? Well, it's var b squared. So it's just var b times var b. As simple as that. And then I can say the data equals df. And I remember to fit my data to my model. And then we can do func model, function model, summary, and print that to the screen. So let's just recap what we've done here. So we're just building a new kind of model here. So we're asking var a and var b, that was d, var a and var d, and then to add to that a function, using a function to transform one of our variables. First of all, we're squaring it, var b times itself, or I can just say **2 to square it, and then taking the log of that value. So I'm completely transforming one of my variables. And here, using stats models, it is this easy to build models. And as I say, for me, to build a model just with a one line of code like that, that's just, that's just fantastic. We see we haven't really shifted, of course, anything as far as our model was concerned. And in the end, though, the idea for me here is to show you just how easy that is. One other thing that you might want to do is it's very easy now. It's been plain sailing up to now because all our feature variables, our independent variables have all been continuous numerical. Can you have categorical variables in there? Stats model says no problem whatsoever. And of course, if you know linear models, you know that that's not a problem. But in the code itself in Python, using Python for your data science, no problem at all. So it says run this line of code. All I've done here is just added a new column, and I've called it cat A, just to simulate the fact that we have a categorical variable now. And one way to do that is the following. I've built some conditions here, and I've said if df target is less than 130, my second condition is the target is more than or equal to 130 or less than negative 130 or up to 130. And then my last one, if it's more than 130, and the three categories I want to put in there is 1, 2, 3. And then I use numpy.select. So this is a little bit of a sort of an advanced thing to do. But as you can see from the code there, it's quite easy. What I've done here, let's just call df. Let's just do the first five rows of my data there. You've seen I've added a cat A there to the end, and all I've based the calculation on is what target was. So this lower values, I made it to 1, and the middle, say from negative 130 to 130, I've made that a 2, and if it's more than 130, I made that into a 1. So of course, this is not part of data science. I'm just generating some extra values here for us to work with. The idea behind what we have now is we have our numerical variables for the prediction of a numerical variable, but we also want to bring in a categorical variable. And we want to bring that in as one of our independent variables to try and predict this. So how easy is it to do? And I've already got it for you there. And it's cat underscore model. So it's SMF again, OLS, target A plus target D. And all we have to do is we still say plus cat A, but we just put parentheses around it and put a C in front of it just to tell stats models here that that variable is actually a categorical variable, and it'll do everything behind the scenes. So what it does behind the scenes, it does what we call it dummifies that model. So instead of those 1, 2, 3, we'll actually have 3 different columns, cat A, Roman numeral 1, cat A, Roman numeral 2, and cat A, Roman numeral 3. So we'll have 3 columns, and we'll just have zeros and ones under there. So if it is a 2 like this, under cat A1, there'll be a 0. Under cat A2, there'll be a 1 to indicate, it's also called one-hot encoding in machine learning speak. There'll be a 1 under there and 0. And that is done all behind the scenes. I don't want to get into that. I want to show you practically here just how easy it is. And if we were to run that, this is what we're going to get. So we still have our intercept. It's still a linear model. And by the way, we've gone up to 96.3. And of course, we've improved things because I was very lenient in the way that I added that categorical variable. Anyway, so we see our R squared, our adjusted R squared there. We see our AIC has come down, but let's look at these coefficients. So I still have an intercept. I still have a coefficient for var A and var D, but now look at what happens to these cat A variables. And all you'll see here is cat 2 and cat 3. You won't see cat 1 there. So why is this so? And that has to do with linear modeling. So if we think about logistic regression, there we're going to express the odds ratio instead of these coefficients. And what we're trying to do is to measure when it comes to categorical variable, we're measuring against some baseline. And in this instance, it's decided that the baseline is the 1, or the subjects that landed up in category 1. That is my baseline. So it's measured against 1. So it's 2 and 3 against that baseline 1. Okay, but that's a bit more involved. But what I want to show you here is just how easy it is to build a categorical variable into your model, and certainly not a problem at all. And let's just visualize this as a last show, and you can see there. If in real life I had a model that does this well, I'd be extremely happy indeed. That just looks wonderful. So those were the 2 very important things: uncertainty and then linear modeling. And of course, because of the time constraint, just for this 1 week, and of course, you can add it to a list if you want me to make specific videos about this to go into a bit of deeper explanation. or just Google it or YouTube it. YouTube is, of course, a fantastic search engine. You'll find all the solutions you want and explanations you want. Otherwise, go back to your old university notes or open a textbook. All the answers are at your fingertips. We live in a fantastic modern world, and it's exciting times indeed. But I can certainly make some extra videos if you're really interested. This was a practical second part here. I just wanted to show you how to use stats models and just how easy it is to work with linear models inside of stats models. Great stuff. I'm going to stop the screen share. Emil, are you still there? Can't you?
Yeah, I'm here. Not a lot of questions happening today, but or at least one question came out that was so confusing that I have to wait to ask you instead. It was from Oliver, where he said, regarding linear modeling, I've been using mixed effects linear models, and I'm unsure how to check the assumptions. Also, how would I deal with what's that word?
Heterogeneous.
And heteroscedasticity.
Or heteroscedasticity. Okay, so that's one very important thing that we didn't tackle yet. So you've built your model. What now? Now you've got to check on a bunch of things. There was a difference between what the actual values were and what your predicted values were. And I touch on that a little bit in the lecture notes, of course, and that's called the residuals. So the errors that your model makes. And you've got to test those. All of this linear modeling, you see, we're basing this on some parameters, and that means we've got to meet certain assumptions. And you've got to test those residuals against a bunch of these assumptions. So heteroscedasticity, for instance, we want this random noise, basically, is what our residuals or the errors have got to look like. And I think that might be a worthwhile thing for me to make a video on after the fact. So let's add that to our list, because when you build a model like this, for those of you who know linear modeling, this is not the end. This is not the end of the road. There's still a bunch of things that we have to do after this to make sure that we've done the right thing. But that's certainly a whole session all on its own to answer that one. But thank you for that, because that's a very important part.
Great. And there was also just one question about what the covariance type means. I think it kept saying non-robustness. Is there any notes on that?
I'm not quite sure what that would refer to when it comes to the R value that we use there, Pearson's, and then of course with our coefficient of determination, R squared there. There's the non-parametric versions of that, Pearson, Tau, Kendall, all those things. And I wonder if we should add that to the list of just a little video to make as well. Actually, if we go down my YouTube video list, I think there is a nice video that explains all of those things. But I think we're getting into deeper things now, and certainly those warrant their own set of explanations. There's someone here on my side that asked about the Likert scale questions. Of course, that's dealing with categorical data. And my answer there was, of course, think about things like the chi-square test for independence, etc. And I think that would be another video that we should add to the list. And if I do make these videos, I won't take up too much of your time. I'll try and make a nice little contained videos about those, because certainly in this 1 week we haven't touched on how to properly work with categorical data. And what I can say to you now, Google some of that. You've got the basics of Python now, and again with a stats model specifically in SciPy, working with Likert scale data, as the question asked there, working with categorical data is as easy as you can imagine it will be. There's a lot of functions inside of the stats module that makes it very easy to deal with those.
And there's a question from Chloe about Bayesian or frequentist statistics. Which one's favorable?
Bayesian or frequentist? Excellent question, Chloe. Chloe, you come up with great questions. So that is a can of worms that you're opening there. You know, what is the best approach? What we're doing, some of what we've done here, or the majority of what we've done here, is this approach of this frequentist approach, this inferential statistics approach, where we take the data and we come to some conclusion, and you can basically flip that around when it comes to Bayesian statistics. So Bayesian statistics, and certainly try and read up just a little bit about that, sort of flips that around, where you have the idea of the world first and some assumptions about the world, and given those assumptions, how does your data sort of fit into there? And I think Bayesian statistics is gaining more popularity. It's, of course, much easier to teach inferential statistics or the frequentist approach. And frequentist, by that just means we've got this bunch of data and we can resample from it. We can do all sorts of calculations on it. It's kind of an easier to understand that, and certainly depending on the field that you are in, but for many fields, that would be the way to go. But the Bayesian approach is becoming more and more used. And so if you go to in your field that you're in, if you read the journal articles, just have a look at if there's a trend, an upwards trend to the use of Bayesian statistics. And as I said, Bayes formula is a very easy formula to understand and look at. So that might just be Bayes equation, B-A-Y-E-S, Bayes equation. Just look at that, just Google that and watch a 2-minute video on that, because from that stems this whole idea. And if you just understand that little bit of probability that goes into that equation, that'll be the start of your journey along the idea of Bayesian statistics. And there are many people who feel that that is a much better approach. And I suppose the future will tell. And in the meantime, we've got this new kid on the block called machine learning, which is another approach to tackling or finding these solutions. Of course, there are Bayesian networks as well, or this Bayesian approach, or this idea of using probability in your approach. Very interestingly, if you look at the history of machine learning, in the beginning we had what we've been through 3 ages basically of AI, of artificial intelligence. The first one was the expert systems, where we believed, when people first started realistically thinking about AI, thinking if we have knowledge and we can build all these rules, if then, if else, if this, if then that, if then that, and if you build a whole tree structure of knowledge, if you put the data in the top and it filters through this whole structure of knowledge, the answer will pop out on the other side. And of course, the world is much more complex than being able to build that kind of rule-based system, what is called an expert system, to use as AI. And then came the probability sort of approach, more in the Bayesian era, where we thought, well, we can't describe everything exactly, but there's probabilities to things being a certain way and things happening and not happening. And sort of we went through this era of this Bayesian approach, and what we are and where we are in artificial intelligence at the moment is very much in what we call the functional age. So we use mathematical functions and optimization. So we have this idea of the difference between, if this is the problem that you're dealing with our prediction and actual values, we can build a cost function, a loss function, and we can minimize that by changing the parameters, and eventually we'll land up on these hopefully optimized parameters, and that is the solution to our problem. So we're very much in this functional age, but a lot of the sort of era, the Bayesian era of that, still works beautifully. And there's whole fields of research as far as those are concerned. So certainly very interesting. And I wonder if people can give us an indication of how many of them use a Bayesian approach in their data science work.
Someone asked if there's any recommendations, if I have any recommendations on how to further the knowledge of Python and machine learning. And I'm not going to lie, I learned pretty much most of my basic machine learning stuff on YouTube videos, because it was neural networks and it's just a description and it just worked beautifully. And then also Towards Data Science is a fantastic blog where researchers and computer scientists are constantly writing about the latest machine learning stuff. So I learned most of my stuff on just YouTube videos and Towards Data Science. And then also you need to get a textbook as well if you want to get deep into it, but textbooks are a bit expensive, so those are all free if you do want to go check those out.
Perhaps we should compile a list, because many of these textbooks are actually free of charge. You know, there's a version on Amazon that you can buy, but many of the textbooks also have the open source version, which you can read online. So I might take the time and compile a little list like that. So I want to support what Emil is saying. It very much though depends on your mathematics background, how quickly you pick it up through YouTube videos or textbook. You know, if if you're quite familiar with these mathematical concepts, specifically in this functional age of machine learning and optimization, then you need half a video and you understand the concept. But if you're struggling a bit there, in that it might take you just a little bit, or people sort of assume that you understand things, and they'll just utter a sentence and assume that you understand what that means. And if you don't, there's this frustration that might develop. So we all know that from teaching research, is that that can frustrate people a little bit. So I would just Google some of these beginner textbooks when it comes to machine learning. Many of them are now open and free online if you don't want to buy the print version. And just pick up one of those and just start reading, and just start. And majority of them are written for Python, and just start playing with it. Of course, both PyTorch and TensorFlow, that will be the two big algorithms as far as deep neural networks are concerned on those websites, Google's website for TensorFlow and then PyTorch's website as well. They're great examples, example code that you just work through. And as Emil said, you just pick it up. You can just pick it up along the way, other than doing something formal. Of course, you can do something more formal. In a couple of weeks' time, I will have that 1-week course on deep neural networks specifically, and of course you can get a degree using this, or you can get your PhD like Emil. So you can formally study these things.
There's a question about data that's constantly changing and how one would deal with that, possibly with linear modeling in mind, considering today's topic.
So I don't know, maybe someone could give us an indication. Are you talking about time series data, that data that changes over time? Or so that's a bit of a vague question that I'm not quite sure what they're asking about that, because time series analysis, depending on the kind of models you work, there's a very robust feature sets in Python for working with time series, or data that changes over time. And audio signals, for instance, is a great example. But any data that changes over time, very easy to code in Python. And maybe there's just so many interesting things that we still have to cover. We need weeks and weeks and weeks. We need to make more and more and more of these courses. Okay. There's one for Kanchu. How much does an undergraduate degree in data science overlap with applied mathematics and computer science?
Cool. Are we going to call it a day?
Yes, sorry, I was just looking here for Python Data Science Handbook. I'm just going to put a link. Where shall I put this link? Let's put it down there. So in the chat session, you'll see me just put a link there, Python Data Science Handbook. Now, the author, Jake van der Plas, remember I mentioned the PyData and SciPy conferences. He's just one of the people that always get invited to speak at these conferences, and he's one of those stalwarts. He's an astronomy, worked in astronomy before, and I think he now works at Google. And he's just formidable in his ability to teach the use of Python and data science. So he's got a book that you can buy. But that book is also completely free online. So if you just follow that link and then click on Python Data Science Handbook, you can buy on Amazon, but you can also read the book. Well, you used to be able to read the book. I just have to make 100% sure. So, you see, this looks like his brand new version. I think the edition. I think the. Okay, so just have a look there because I'm quite sure you used to be able to read that. But let's. I'll try and spend some time and get a couple of free online books. I'll make that little list before tomorrow. Okay, yes, Emil, let's call it a day then.
Perfect. Thank you so much.
So for tomorrow, someone asked there, yes, sorry about this last, but someone asked there tomorrow that there's no exercises tomorrow. Tomorrow, I'm going to use the time to introduce you to a wonderful service. If you're really interested in machine learning, this is really one of the major places to go with a lot of free tutorials, a lot of support, and a lot of other benefits. I won't say what it is, but I think many can guess what service I'm talking about. But I'm going to introduce you to that service, and we're going to use some live data, and we're going to run through some of the aspects that you need to consider when you create a machine learning model.
Very excited. This is going to be the stuff that I'm also constantly doing. So excited to hear what you have to say.
Excellent. Thank you.
All right.
Thank you, Jan.
Thank you, Kancho.
We'll have that 6 o'clock session. If you have questions on career path, postgraduate degrees, postdocs, etc., please, or undergraduate degrees too, please do come to that. We may not have every answer, but we'll tell you where to get your answer if we can. Thanks, everyone. I'm going to close this session.
Thank you. Thank you, everyone. Bye.